The history of atoms. 500 BC, that's 2,524 years ago. Leucippus, whose name is pronounced many different ways on the internet, and his pupil Democritus. They said that atoms were indivisible, so you couldn't cut them in half, that they vibrated continuously, they would never stop vibrating, and that between them there was space. This is going to come back later. And also, yeah, always in motion, space between them, indestructible, spheres. They did also say that there were some different shapes, but we kind of forget the bits that they said that were wrong and just concentrate on what they got right. 2,300 years later, things got slightly better when a man called John Dalton, 1803, so that's 221 years ago, he said, yes, they were solid spheres, just like the atomos, which they used in Greek, the Greeks, Democritus and his teacher, they were different sized spheres. Elements were all one size, and if you were a compound, you were two different sizes of atoms. So this could be, in Dalton's theory, sodium chloride. Sodium chloride, sodium chloride, sodium chloride. The salt that you eat and is in salt water. Now, not really. We've found out things better, and now it's much better to say, oh, this is carbon monoxide. Well done, John. You got carbon monoxide, right? Next came J.J. Thomson, 1904. So that's 120 years ago. And he said, hey, now that I've discovered negative electrons, these guys here, and Goldstein has discovered positive stuff, then I'm going to put both concepts together into my new atom, which is made with my negative particles surrounded by positiveness. A little bit like if you make a pudding, a dessert, made out of plums, dried plums. You bake this pudding and the plums will float around in amongst the flour and sugar and other things that make plums. And so you've got smaller atoms and bigger atoms with possibly different numbers of electrons and positive charge. The plum pudding model. Just a few years later, Ernst Rutherford completely crashed the plum pudding by getting some alpha particles discovered by Mrs. Curie and others, Mr. Curie, and he took this alpha particle, which he knew was positive, and he shot it at gold atoms. And of the 2,000 times he shot it at gold atoms, they just went through, and he shot it, and this is what he expected, because he'd made the gold very thin by hammering it to very, very, very thin. Less than 1,000th of a millimeter thin, because gold you can do that too. But then one in every 2,000 came back. And he said, hold on a minute, if they're just going through most of the time, oh, that one didn't go, that one went weird. Most of the time they're just going through the atoms, and then one in every 2,000 they're bouncing off or diverting at weird angles, or diverting at very weird angles. Then he said, the positiveness must be all in the center. He had discovered that all of the pluses were in the middle, and that that's not quite in the middle, hold on, and that all the other stuff, however many pluses there were, he wasn't quite sure, maybe more for more bigger atoms, and that the other stuff was hanging around the outside, and that was the negative stuff, the electrons. Here we go. Electrons just hanging around the outside. However many pluses you have, the same number of negatives. And there's your JJ's, Thomson's electrons, and all of the positiveness, protons, that Goldstein discovered is all in the center. That was the only way to have the positive alpha particles, which are the insides of heliums, but he didn't know that yet. The positive alpha particles bounce off when they hit something very, very small in the center, about the size of a pea, inside your living room. That's how small the nucleus was. Then along come Mr. Niels Bohr, and he said, yes, I agree with you that all J.J. Thomson's electrons are around the outside of the nucleus, but they're not just floating around, they're in actual sort of circles. Just like kind of Mercury is going around the sun, with the difference that there's enough room for two Mercuries, two electrons, in the first circle. And the second circle, here we go, drawing, second circle, or orbital, or also called shell. There was more room, so you could put more electrons in, and they tend to go around in twos. And they could orbit the nucleus. Hold on a minute, I've got more electrons going. My electrons, I've only got 2 protons, so I should only have 2 electrons. That's helium. And now I've got 2 and 8. So I've got 10 electrons, so I need 10 protons squashed up in the middle. Hold on. 3, 4, 5. Okay, 6. I'm going to draw 10, 7, 8. There's 10 protons in the middle because there's 10 electrons going round the outside. Tiny, tiny nucleus. The outside filled up with space and the electrons, hence the space between the atoms thing that I told you about earlier. It's actually, no, the space is between the electrons, and there's the next atom of, hold on, this one's got 10 electrons, 10 protons, so it's going to be neon. We tend to only draw the outside electrons because they're the ones that do the chemistry. Here, there's an extra bonus. I'll draw the inside ones. And there's a nucleus here, and it's got 10 pluses. I haven't got time. Next came Erwin Schrodinger. There's a couple of dots above his name there. 1, 2... Mr. Schrodinger in 1926, very busy years around here. He said that electrons are waves and not particles. We've since found out that there's sometimes waves, sometimes particles. And he said that there was a probability that this electron was somewhere around this kind of place, and that this second electron here was somewhere around here. And so where exactly a electron it was probabilities. It's mostly here where I draw the E, but actually all the electrons are waves up and down, and somewhere around there. And then there's another one around there. And so electrons are waves, Schrodinger, and you ended up with wave-particle duality coming in. Chadwick also invented the neutron. He discovered the neutron, and he found out there's approximately as many neutrons as protons in the nucleus. They kind of keep the protons separated because plus and plus, they spread. They don't want to be next to one another. Electrostatic repulsion inside the nucleus. The neutrons keep the protons apart. You can have more neutrons or less neutrons, but mostly, apart from hydrogen where you only get 1 proton, it doesn't need neutrons. But there is some hydrogens that have neutrons. Deuterium is the type of 1 in a billion hydrogen that has 1 neutron, and tritium is the 1 in a trillion hydrogen atom that has 2 neutrons, but most hydrogens only have 1 proton. All other atoms have approximately the same amount of neutrons as protons and sometimes more neutrons than protons, and the number of neutrons can vary, and that's called isotopes. Cool! Press subscribe and like. Bye!